It took me a while to get to this.
Okay, it's my pleasure to introduce Ilijas Farah from York University. He has made significant contributions to many areas of binary set theory. In recent years, he has pioneered a vibrant research area in the intersection of logic and operator algebras based on continuous model theory. While classical model theory focuses on discrete structures, continuous model theory offers truth values in the interval 0, 1, where propositional connectives are real value functions and quantifiers are infinite. But I have a lot more information here, but let me just say that he gave an invited address at the ICM in 2014 on logic and operator algebras. So that means we have to take him seriously.
Thank you. I would like to thank Chris and Dave for invitation and for a wonderful introduction. Now, I have to disappoint maybe. I'm not going to mention continuous logic at all in this talk. Well, not explicitly anyway. So anyway, as you can see, I'm starting with a linear algebra test question. Let me to illustrate it once again. Here we have this K by K matrix, which you may recognize is just projection to the constant vectors. And question is there M, single M, such that for every K, there is a K by K matrix, which is within 1/100th from AK in the operator norm. And yet, in every row and every column, BK has at most M non-zero entries. So of course, once we decide what M is, I can take K to be 2 to 2 to 2 to 2 to M, and it just doesn't seem like it should be the case. We'll come back to this later on. But now, so here is my talk. And again, okay, I have another exercise. Which I mentioned to the students, so they're a little bit ahead. But here's the question. Fix a Borel subset of three-dimensional space. You can take G delta set. It doesn't have to be complicated Borel set. Project it to the plane. Take the complement. Project that to the line. So the question is, does that set necessarily have to be Lebesgue measure? It sounds like a simple real analysis question, right? Okay, we'll come back to that as well. In the meantime, I'll start with a large-scale geometry. Okay, so this is a subject that I just started. I'm not really in this subject, so I'll try to answer easy questions, but if you ask me complicated questions, I may not be able. The idea is that coarse geometry studies large-scale behavior, geometric behavior of metric spaces. Here is well, the main definition of a coarse map. As you can see, it resembles the definition of uniformly continuous function, except that a few things are switched. First, what matters is the large values of K and L. And second, in conclusion, K and L are switched. So basically what it says is that 2 points which are not too far away ascend to 2 points which are not too far away either. But this is different from quasi-Lipschitz or so. Let's just look at examples. So here are examples of two functions from reals to integers. Just the smallest integer greater. Sorry, yeah, no, largest integer smaller than x, and second one is x squared. Now only one of these two functions is coarse, and it is actually the one which is not continuous. Because if you just take L to be K plus 1, definitely this is not going to be worse than that. But x squared is continuous, but not a coarse map. Two spaces are coarsely equivalent if they are coarse mapped from one to the other and one going back. So their composition is not the identity, but it's not too far from the identity. Uniformly, it is not too far. So this is, we have a category of metric spaces with slightly different morphisms. Let's look at the first example. R and Z are coarsely equivalent. Right, so basically one of the functions is this one here. The other one is simply the identity embedding from Z into R. And both functions are going to be close enough. And the idea is, if you just look at the the integers, if you zoom out sufficiently, they look just like real numbers, just like a straight line. And similarly, complex numbers and z squared are coarsely equivalent. Okay. Now, the fact that reals and integers are equivalent just doesn't sound right. So I'll stick to spaces which satisfy additional assumption. Space is uniformly locally finite if it has the property that if you look at n balls for any fixed n, soup of their cardinalities is bounded. Right? So reals are definitely not, because every open ball is infinite already, but in the integers, right, actually soup is given by the diameter pretty much. Okay, so some important examples of uniformly locally finite matrix spaces. If you take a graph which is k regular, right, which just means that every vertex has only k immediate neighbors, and look at the path distance, then the cardinality of n ball is pretty much n to the kth power. So it is uniformly bounded. And very important example, finitely generated groups. Right? Take a finitely generated group, take a generating set, and look at the Cayley graph. Right? It is a regular graph, and space is uniformly locally finite. Now, I don't know if I need to define Cayley graph. Right? So 2 points, the vertices are elements of the group, and 2 vertices are adjacent if and only if you can multiply one by one of the generators and get the other one. So for example, the free group with 2 generators looks like this, right? So if it's like a tree, so it is very different, even in coarse sense, from the integers. Now, if you take any 2 generating sets for your group, you get coarsely equivalent spaces. Metrics are slightly different, but they're sufficiently close. You can just check that. Okay, now, okay, the plan here is to try to understand coarse geometry by looking at operator algebras. So let me just quickly go over definitions. We have a complex Hilbert space. So all Hilbert spaces are complex because I want my spectral theorem. Also, all operator algebras are going to be self-adjoint. So for any operator, also the adjoint to that operator is in the algebra. L2 of x, given any set x, L2 of x is just Hilbert space whose basis is indexed by elements of x. So they're delta x for x and x. The B of L2 of x is the algebra of bounded linear operators on L2 of x. And one way to think about those operators, which is actually not terribly wrong, is just to think about, we have essentially big matrices indexed by x cross x. And if you have an operator T, if this is x and this is x prime, this is really the matrix coefficient T delta x prime. So not every matrix like this is bounded operator, but every bounded operator is given by a matrix like that. And 2 kinds of operator algebras. First, cyst algebras. So those are self-adjoint algebras which are also closed in norm topology. And even more closed, von Neumann algebras, again, self-adjoint and closed in the weak operator topology. Just one easy way to think about weak operator topology is it's really pointwise convergence if you look at these matrix coefficients. So a net converges to an operator if and only if all the matrix coefficients converge pointwise. Okay. And now the plan is to start from a metric space and associate an operator algebra to it. And here it is, it's uniform row algebra, named after John Rowe, who unfortunately died actually in March this year. So for an operator T, again, think of T as a big matrix, its support is set of all those pairs x, x prime, such that the corresponding matrix coefficient is non-zero. And the propagation of T is supremum of distances between pairs, elements of pairs which are in its support. So for example, if you look at L infinity of x, which is all operators which are diagonal operators, or all the ones which are diagonalized by the standard basis, propagation is 0. Because pair x, x prime is in the support if and only if x is equal to x prime. Next example, if you take L2 of z and look at the unilateral shift on the basis, propagation is 1, because everything is just moved a little bit. Okay, and now propagation behaves reasonably well with respect to algebraic operations. If you take adjoint, you just flip the whole thing and conjugate, so propagation is unchanged. If you add, you just have maximum propagations. If you multiply, you just add them up. So basically, you can look at the algebra of all operators with finite propagation. It is self-adjoint algebra of operators, and its name is in this tiny font because I think it's a very silly name. It's called algebraic uniform row algebra. It's algebraic algebra. But anyway, so that's one with square brackets. Now, it is not norm-closed. One reason for that is the following. If you look at all finitely supported operators, they're all in the algebra, because if you have a finite set, then the maximum is still finite. Therefore, you can get every compact operator as a norm limit of operators in this algebra. So we take norm closure and get uniform row algebra. There is also so-called row algebra, and almost everything that I'm going to say applies to it. It is the version in which we look at operators which are valued not in complex, these coefficients are not in complex numbers, but they're really compact operators in some prescribed Hilbert space. But just this is easier, although the other one is more important. Actually, quite a bit of motivation comes from the row algebra, but I'll stick to this one. Now, you see, this is a C-star algebra. It is definitely not closed in weak operator topology because compact operators are weakly dense. But it does have some features of fundamental algebras. So let me say what are properties. First, it is, by definition, it is a C-star algebra. Second, all the compact operators are there, as I said, because all the finite rank operators are there. Three, L infinity of x is there, because these are operators with propagation 0. And it is also a maximal abelian subalgebra, or in short, it's called massa. It's very nice maximal abelian subalgebra. There is a conditional expectation from the whole algebra to it. You just basically erase all but the diagonal coefficients. And another property that if x is uniformly locally finite, which remember just means that soup of cardinalities of all n balls is finite, then the algebra is generated by L infinity of x together with a countable subset of its normalizer. Now this is really an exercise in combinatorics. Let me try to draw a picture. Just you see, think about x. If x is z, remember the shift has propagation 1. If you think about operators with propagation n, they're just wandering n away from the diagonal. And now any set that has a finite width can be partitioned into finitely many sets, such that each one of them has only at most one entry in each row in each column. And those really countable finitely many partial isometries. And if you take all of them, you generate the whole algebra. So basically, L infinity of x is very visible somehow in the middle of the algebra, and we'll come back to that. Okay, so here is the problems that I'm concerned with. First, one definition, right? Row corona is obtained by taking uniform row algebra and modding out the compact operators. Now, all of those are subalgebras of so-called Colloquium algebra, which is obtained by taking all bounded operators and modding out the compacts. And Colloquium algebra is quite important, in KK theory, in sorts of, in different applications of operator algebras. But it's also very unruly in many ways that are going to show up a little bit later on. But anyway, I said the questions. So suppose X and Y are uniform locally finite metric spaces. And look at the following three assertions. X and Y are coarsely equivalent. 2, their uniform row algebras are isomorphic. And 3, their row coronas are isomorphic. What is relation between? What implications do we have? Now, if you assume 1, it actually doesn't imply 2 or 3. It really implies Morita equivalence of these algebras. But it's close enough to isomorphism so that I'm not going to worry about that. Really, the interesting implications are going up. Right? So if C algebras are equivalent, how similar are the spaces? And the original motivation for that question in particular comes from Baum-Cohn's conjecture, which is, well, something that I cannot say that I understand very well, but basically question is, does K theory of this algebra reconstruct K theory of X? To me, as a pure mathematician, that's the question by itself is interesting, but there is more to say about the motivation. So I'll spend first some time talking about the 2 implies 1, and then I'll move to row coronas. Any questions so far? All right. So this was initiated by Jan Spaklo and Rufus Willett. So then they notice the following. If you have isomorphism between 2 of these algebras, it's actually automatically implemented by unitary. This is really an easy exercise. So I'll just say that it just makes it easier because then you just need to understand isomorphism. You have this concrete, very concrete unitary. You just have to understand where it goes. And here's what they proved. For uniform locally finite spaces, X and Y are bijectively coarsely equivalent with the obvious definition, if and only if the algebraic algebras are isomorphic, if and only if uniform row algebras are isomorphic, but with an extra assumption, isomorphism sends the Cartan massa to Cartan massa. Because then you can actually just read off what the functions are. And in the proof of 2 implies 1, the main idea is that if you have isomorphism, then you can prove that it has coarse-like property, namely that if you look at all operators of propagation at most n, propagation of their image is uniformly bounded. And the trick is, because this is algebraic, you can do whatever you want. You can basically scale things and change them and just easily get contradiction from if you assume that this fits. Okay, but let's see how do we get from the algebra from algebra isomorphism to coarse equivalence of spaces. So suppose that we have isomorphism between C algebras and fix a unitary such that the conjugation by that unitary implements the isomorphism. And now look at the following sets. So if you here's X, here's Y, right? So unitary sends L2 of X to L2 of Y. Now for any point here, if you look at the image of unit vector, it is some unit vector. Look at its coefficients, and look at what is the maximal coefficient of that vector. So that splits our X into some pieces, and do the same thing on the Y side. Now, question is, does this stop? Can you find a large enough n so that both X and Y are exhausted by this? If this happens, we say that phi is rigidly implemented, which is probably not the best of phrenologists, but okay, got stuck. Now, in that case, Spaklo and Willett proved that actually X and Y are coarsely equivalent. This requires some argument. now, as I should have said earlier, this is joint work with my postdoc Bruno Braga and my former student Alessandro Vignati. So what Braga and they proved is that actually slightly more, there is an approximate coarse-like property. So you see now, if you know propagation of an operator, then for every epsilon, we can uniformly approximate it by operator of fixed propagation. And the proof is basically bare category theorem. Just once you set up things properly, it's really just bare category theorem. Right. So if it is implemented rigidly, then we are fine. But you know, can it happen that it's not? Okay, so ghosts. Guolian and Yu define an operator to be a ghost if, when you look at its matrix coefficients, they converge to 0. Namely, at most, finitely many of them have absolute value greater than any given epsilon. So, of course, all compact operators are ghosts. But, okay, do we have ghosts which are not compact? Well, that's an exercise. What do they look like? I'm going to give you an interesting ghost, not just any ghost. So here we come back as I promised. So here is slightly more complicated version. Remember, we had these matrices AK, and question was to approximate it up to 100, but actually you can do it up to any epsilon. The fact is that for any given epsilon, there exists some number m sub epsilon, so that you can choose matrix B epsilon K, which has at most m epsilon non-zero entries in each row in each column, and yet it approximates AK up to epsilon in the operator norm. And now, if you can find those matrices, then actually, regardless, we can find them. Sorry, if you just put your matrices AN on the block diagonal, this is a ghost. The reason, the purpose of this B epsilon case is going to be clear in a moment. So I'll move on to something more interesting. There is well, this is a counterexample, coarse counterexample to Baum-Cohn's conjecture, and it involves a sequence of so-called expander graphs. Now, okay, the story goes that actually it was in Toronto. Eberhard Kirchberg was giving a talk, and some student asked about some very technical term. I think it was Kishimoto spectrum or something, and the answer was every mathematician should know what that is. So I don't know if anybody is going to ask about expander graphs, but since I'm not Kirchberg, I'll have to draw a picture at least. But I do think that everybody should know what it is. Sequence of expanders are finite graphs whose cardinalities are increasing, and they are all, let's say, 3 regular, just to keep it simple, but very highly connected. So they have the property that if you look at one of those graphs, if you take subset of the vertices whose cardinality is not greater than 1/2, and if you look at all edges connecting those vertices with those in the complement, the number of those edges is at least epsilon times the cardinality of your set. So they're very highly connected. Now, if you have sequence of such graphs, then you just build this metric space X from Vns. So just put different Vns to be at infinite distance, and at each Vn just take the graph distance, and look at the normalized Laplacian. So A is the adjacency matrix. Now note, adjacency matrix for a graph has propagation 1. And this is just the identity, so it has propagation 0. So all of these operators have propagation 1. Okay, their direct sum also has propagation 1, but it has more than that. Because of the expander property, this operator, which is a positive operator between 0 and 1, it has 1 in its spectrum, but 1 is an isolated point in the spectrum. So if you take higher and higher powers, this sequence converges in norm. And therefore, this converges to a projection. And projection is projection to the kernel of the Laplacian, which is exactly projection to the constant functions, which is exactly these ANs. So my matrices Bn are really given by sufficiently high powers of these. But I have no idea what they look like. I mean, it's, you can construct expansions probabilistically or from property T group, but what they look like exactly, it's hard to say. Okay, but what they give us is coarse metric space, which is uniformly locally finite, and it has ghost projections, which are not compact. Now, why does that matter? Well, remember, I just erased it, but back to our question. If we have a coarse space and maximal abelian subalgebra is said to be ghostly if there are countably many non-compact ghost projections whose sum converges to identity in strong operator topology. It's also closed in weak operator topology, and together with its normalizer, it generates the algebra. So the point here is that it looks like L infinity of X to some extent, but it has these ghosts which definitely don't have in L infinity of X. Now, why does that matter? Well, what Braga and I proved is that if you have isomorphism between uniform row algebras, which is not rigidly implemented, namely those Xn's never exhaust X or Yn's never exhaust Y, then one of these two spaces has ghostly massa. And once you see this, it's actually very easy, as I said, to prove it if you remember all the definitions. But it took some time to understand what exactly is going on. Now, for all the nice spaces, there are no ghostly massas because there is this U has this amenability property, property A, which excludes existence of ghostly massas. But we don't know whether this can happen still. But there is this example from the previous slide. So we can modify it a little bit and get almost there. So if X and Q are the space and that non-compact ghost from Higgs-Laforgue Scandalis example, there are unitaries which are in L infinity of X, such that if you conjugate that projection with different powers to a unitary, you get projections which are almost orthogonal. And if you just remove finite rank operators, they actually end up converging strongly to the identity. So you can use axiom of choice to extend this to maximal abelian subalgebra, but it's not clear whether one can get it to be closed in the weak operator topology. So it's not clear whether we have example here or not. Original Willet's example was actually coming from property tau group, but he proved that in his case this doesn't work. Well, this other case is vague enough. There are all sorts of expanded sequences that we don't really know whether it can be pushed or not. Okay, any questions? Okay, so let me just now wrap up this part of the talk. If we have metric spaces X and Y, and neither one of the algebras contains a ghostly Cartan massa, or one of those spaces coarsely embeds into a Hilbert space. I never define what this means, but you can guess. Basically, it's coarsely equivalent to a subspace of Hilbert space. And now, if you think, what do you mean? Of course, every subspace of Hilbert space is a Hilbert space. Well, I'm talking about metric subspaces here, not Banach subspaces. Then X and Y are coarsely equivalent. There are examples of spaces which don't satisfy our assumptions, and we don't know what can be said in general. Now, original idea when Braga and I started working on this was that we wanted to extend Spaak-Polar-Unit results to coarse spaces which are not necessarily metrizable. So just like the definition of uniform space, you can define a coarse space abstractly by just axiomatizing what entourages look like. And question was, and you can define uniform row algebra. And question was again, is there rigidity theorem? And we have, all right, so actually before one, reasonable example of such a space, take a group gamma, which is not finitely generated. Like to take, for example, 3 group with infinity many generators. And now entourages, uniformities are just defined by taking different finite subsets and looking at corresponding Cayley graphs. So this defines your core structure, which is not metrizable. And the question is, how much does that core structure tell you about your group? So, okay, here's what we have. So if X and Y are core spaces, and there is an isomorphism between uniform row algebras, which is first rigidly implemented, and second, forcing absolute. I'm not going to define what this means properly. I'll just tell you that it means that it somehow persists moving to different universal set theory. But if you can force and still recover it. Now note, this is not always meaningful. In this case, it is. If you know X and Y, you can recover the algebras. Isomorphism is more difficult to recover in general, but this one is given by unitary. And unitary is just continuous function that you can just continuously extend. So it's meaningful. And if isomorphism satisfies this property, then they are coarse equivalent. Assumption is satisfied by some absolutist theorems if X and Y are metrizable. In general, we don't know whether this assumption is necessary or not. So there is a consequence that for example, Martin's axiom implies that if X and Y are small and their uniformities are generated by small sets, then we have a rigidity property. Right? But the question was, what about coronas? Let's remember, we get corona by modding out the compacts. And for example, in that space of Higson, Laforgue, Scandalis, if you look at this ghost projection, that actually itself corresponds to a corona of another space, and to uniform row algebra. But in that case, corona is just going to be L infinity mod C0. There is nothing else in that. But sometimes you get more things. For example, in case of Z, you get interesting algebra. So the question is, how much does isomorphism between coronas tell you about isomorphism between uniform row algebras? And okay, if I put it this way, this is a wrong question. Let me just say what the question was. So can we prove that if coronas are isomorphic, then so are the uniform row algebras? Essentially, there are simple examples that just refute obvious thing. But real question is, can we find cofinite X prime and Y prime so that those spaces are algebras are isomorphic? Okay, so let's look at properties of the uniform row corona. Just like the algebra, it is a C-star algebra. It's actually non-trivial fact that the quotient of C-star algebra is 3 and C-star algebra. L infinity mod C0 is a massa. It's Cartan massa. And again, if X is uniform locally finite, the corona is generated by the massa plus countable subset of its normalizer. Now, the fact, the item number 2, this presence of L infinity mod C0 is a bit of a red flag from the foundational point of view, because that algebra is quite notorious for having very few properties which one can prove with LFC. Almost everything about it is independent. So here's a classical example. Walter Rudin proved that under continuum hypothesis, this algebra has 2 to the continuum many automorphisms. And Sakharov and Shelach proved that in some model of ZFC, all the automorphisms of L infinity mod C0 are the obvious ones. Namely, they're induced by bijections between cofinite subsets of natural numbers. So there are almost permutations. And there are only continuum many of those. So definitely most of Rudin's isomorphisms are not like that.
Can you refer to us what is relative consistent?
It means that you know, if you assume that ZFC is consistent, then this is consistent. Because you know, we can never prove that ZFC is consistent. I mean, the only situation in which we can prove that ZFC is consistent from ZFC is if it's inconsistent, and we can prove anything. So we just have to be careful. Just, you know, there are some logicians in the audience, so I just have to make sure that I don't say anything false. Right. Any other questions? Right. Okay, so let's go back to my exercise. So fix a Borel subset of the three-dimensional space, project it to the plane, take complement, project again to a line. Is it measurable? Measurable. Okay, so consider a statement that yes, it is always measured. So is this true or false? That's a simple question. Well, first, you cannot prove it in ZFC. And again, as Vitaly just asked and I pointed out, maybe you can, but if you can, that's terrible. So we don't want to think about that. You cannot disprove it in ZFC either. But even worse than that, you cannot even prove that it is independent in ZFC. You have to assume some large cardinals to prove that. So this is as bad as it gets, really. And in operator algebras, there is no natural statement that has this status. But some statements come quite close. So here is one of those. The Colloquium algebra, right? So it's the quotient of bounded operators and also compact operators. So I like these two titles. There is a paper by Chris Phillips and Nick Weaver, whose title is "The Colloquium algebra has outer automorphisms." And so they construct an automorphism which is not implemented by unitary. And then a few years later, I had a paper called "All automorphisms of the Colloquium algebra are inner." So this may seem like showing that ZFC is inconsistent, but it's not that. Basically, you know, they were not completely precise with their title. What is going on is that they used continuum hypothesis. And of course, writing continuum hypothesis implies that Colloquium algebra has outer was too long, I guess. But once they had their title, I had no choice but to say this, right? So now we're stuck with it. But anyways, so basically this is a question which was actually asked about the same time when Shella proved his theorem, and his methods definitely can be tracked down. I mean, they form the seed of the whole subject. So there is independence in operator, in mainstream operator algebra. But the reason why I'm mentioning this is that at the moment you start modding out, going to coronas, you can expect something like this to happen. So let's see what does happen. Right. So here's the conjecture. Suppose that we have two uniformly locally finite metric spaces. Now, assuming PFA, which is the same axiom pretty much that I used to prove that all automorphisms are inner, then isomorphism between coronas should imply almost isomorphism between algebras. Namely, if you just remove finite subsets, remaining algebras are isomorphic. And then by our other results that X and Y are coarsely equivalent. Second part, continuum hypothesis should imply that there are two spaces. I have 10 minutes. That there are two spaces whose coronas are isomorphic, but they are not coarsely equivalent. And so basically, there should be some independence. And I could ramble about why these axioms. There are reasons for that, but that's maybe a subject for different talk, which I would be happy to give at some other occasion. But let's just stick to this. So basically, the bottom line here is that conjecture is, there is some independence here. Okay, so let's see. Right, so the first result, using my own results and also more recent results by Paul McKenney and Alessandro Vignati, Braga and I together with Vignati proved that under PFA, if we have x and y, which are, as always, uniformly locally finite metric spaces, and all Gauss projections are compact, or if just one of them coarse embeds into Hilbert space, then if coronas are isomorphic, x and y are coarsely equivalent, just coarsely equivalent. Now, this is not the right theorem. I mean, it's correct. Proof is correct as far as we know, at least. But you see, to me at least, the right theorem in this subject should look like this. Just draw it. So here we have corona of x and corona of y, right? So there is an isomorphism. Now here are the algebras. Here are the quotient maps. Well, there should be a homomorphism between these upstairs algebras, which lifts phi. That's not quite the case, usually, but some reasonable map which does the trick. So maybe you want to remove finite subsets of x and y or something like that. But basically, there should be a lifting theory. And this is how I wanted the proof to look like. But unfortunately, so at this point, we can just basically do some sort of a halfway lift and then argue the way that we argued before, that actually we can construct coarse equivalence. Actually, Vignati posted recently on Math Overflow a question, which is a quite curious question about untwisting co-cycles. That would imply that, at least, I mean, positive answer would imply that in many cases there is a right lifting theory. We can prove that untwisting in case of groups with Kelly graphs, basically for hyperbolic groups, at least for free groups, we can prove it, but even for z squared, question seems to be untractable to us. All right, so much for that. Now next, and now this is, you see, we actually were able to improve our earlier results. Again, assuming PFA, if x and y both have use property A, this is a strengthening of no Gauss projections, which are not compact. Then coronas are isomorphic if and only if you can find cofinite subsets such that x prime and y prime are bijectively coarse equivalent. Now, you see, this is, you know, it may sound funny at times saying this is strengthening our result because we have this assumption PFA, by certain mathematical arguments, PFA can be removed if you just, okay, let me just, I don't have implications. So if you have, if you assume that algebras are isomorphic, well then definitely the coronas are isomorphic. And now by our result, using PFA, x and y are coarsely equivalent, but then it means that you have implication going this way, but it turns out that these statements are so simple logically that you don't need PFA. So simple implication is true without anything. Right, but the real question is, are there uniform locally finite spaces x and y such that this statement is independent from ZFC? We don't know, but you know something. Right, so remember, this was my conjecture, that it should be true, and also part of conjecture was that somehow continuum hypothesis implies that algebras are isomorphic, but something else implies that they are not. And then necessarily spaces cannot be coarsely equivalent, because coarse equivalence you cannot change no matter what axioms you assume. Okay, so and this is where so far all the logic in my talk was set theory, and now we come to other. So there is my former student Said Ghassemi proved. Let me actually say what he proved exactly. Actually, no, yeah, I can say it later because I already see it. So basically, by using his results, we can prove that there are two discrete metric spaces X and Y. They're not uniformly locally finite, but they're discrete. And they're quite stupid spaces, actually. I mean, they're not exciting. You wouldn't want to see them except for the purpose of this theorem, I guess. Such that the assertion that the row coronas are isomorphic is independent from the FC. Now, proof uses both set theory and model theory, and both there are two directions, and they're both used, used non-trivially. Let me tell you what the spaces are, because it's kind of funny. They both look the same. So X is just a disjoint union of spaces Xn. And again, just different spaces are at very far distance. Actually, this is a graph. You can think of this as a graph space. And Xn, it has some cardinality, I don't know, let's call it K of n. And the graph is simply the complete graph. So all points in Xn are at distance 1. And you just need to choose Kn fast enough. Y is of the same sort. Now, what does uniform row algebra look like? Well, you see, every operator that stays inside Xn has propagation 1. So really, the part with Xn really corresponds to Kn by Kn matrices. And so all possible operators there have propagation 1. So really, the algebra, so the uniform row algebra, is just a product of all of these matrix algebras. But also compact operators are there. You cannot avoid them. It's algebra generated by this. Okay. Now, when you mod out the compacts, what do you get? Well, it is product of matrix algebras modulo the direct sum. And because the compact operators are just causal finitely supported ones. And so, now I can tell you what Said proved. You see, this is what model theorists would call reduced product. And there is quite a useful theorem by Pfefferman and Watt, which tells you that you can compute the theory of this object if you know all those theories. And Said proved a continuous version of Pfefferman-Watt. So all that you need to do is pick a very fast converging, fast growing sequence of matrices so their theories, and these are those continuous theories, actually converge. And then if you take faster subsequence, limit is the same, and the theories are the same. But then Sherlock and I proved that these models are always countably saturated, which just means that under continuum hypothesis, they are going to be isomorphic. And then Said also proved that which is even more interesting result, I guess, that under some other assumptions, well, proper forcing axiom basically, two algebras like this are going to be isomorphic if and only if sequences, corresponding sequences are equal modulo finite. You can just drop first finite many matrix algebras, and the rest has to be exactly the same. But again, these spaces are badly not uniformly locally finite, and we did try hard to get examples, but we don't know. And okay, so I'm just going to finish with a few questions. So you mentioned some of them, so I guess I can just stop here. Thank you very much.
Questions for the speaker?
Sure.
First one is fresh, so if you go to the previous page.
Okay.
Here. Is there any way to try to describe such discrete metric space effects for which you wouldn't have?
You mean pairs? Well, okay. One thing is model theory again. I mean, if the coronas have different theories, they're not going to be isomorphic because theory you cannot change by no matter what you do.
I'm writing in terms of metric spaces themselves, properties.
Well, of course, I mean, if you want if and only if, which I'm sure you do.
Strong sufficient.
Well, I mean, there are things like, there is asymptotic dimension and things that you cannot change, right? So if you have free group with, free group and z squared, that they are not going to be. So definitely there are some properties. Remember, this is all about transferring properties from spaces, actually from coronas to spaces. And there are quite a few properties that go from spaces to coronas, like asymptotic dimension, hyperbolicity and things like that. Now,
So for example, suppose there are calligraphs.
yes.
So is there a condition for the groups whose calligraphs are considering this?
Okay, I mean, okay, so again, if you take z to the third and z squared, but that's kind of silly, that's not what you meant. I don't know enough geometric group theory to say anything meaningful. I'm quite sure that there are many examples, but I doubt that there is any sufficient and necessary condition. You said you had two questions. Yes.
My other question was, what is the reference to this fascinating projections?
Oh, ghosts. You mean the Higgs and Lafroig standards?
No, the second three which projects.
Oh, that. Okay. What's the reference? Let me see. It should be in every set theory book, but it's not. Let me see. Well, basically, yeah. No, I know. Well, what is?
What are the names?
Oh, okay. Names. Okay. One direction is Gödel. In Gödel's constructible universe, he actually got. I mean, if you just bump it up one, start from R to the fourth, you can actually end up with well ordering of the reals in that way. The other way around, I think that the right reference will be Martin and Soloway. So they prove that if there is a measurable cardinal, then all those sets are Lebesgue measurable. And one should mention Lebesgue, who actually claimed that continuous images of Borel sets are Borel, which is false, of course. If that was true, it would be easier. Exactly, so we figured it out. But then, basically, it's really determinacy. If you have sufficiently large cardinals in the universe, then you have projective determinacy, and it means that all of those projective sets that you can obtain by these continuous image components, all of them are Lebesgue measurable and everything that you can imagine. Hugh Woodin had this in notices of the AMS paper called Continuum Hypothesis, Part 1. I think it was just called that. And there he discusses this. I can try to think of a better reference. Maybe Kanamori's book about higher infinite should have something about that. Yeah, sure. It's large cardinals. Yes. And of course, there is Soloway's model that if you have inaccessibility, you can go to model where all sets are Lebesgue measurable. And the last, actually, the most spectacular thing, if you ask me, is that you need large cardinals. What Shellac proved is that if all projective, even if all sigma 1,3 sets are Lebesgue measurable, then there is an inaccessible cardinal floating somewhere, which is why you cannot prove consistency without going beyond ZSC.
Any other questions? Let's thank the speaker again.